So as we take a look at Module 12 for ME111, System Dynamics, we're going to take a look here at this first module going over some compensator design. So some objectives for this chapter we have here are: one, we're going to learn how to design a compensator using either a root locus or frequency response plot. Two, we're going to take a look and use the open loop frequency response plot to design a controller. Three, we're going to analyze the effect of the time delays on the system response. And four, take a look at MATLAB and Simulink for methods for utilizing these as well. So as we break down chapter 12, it comes into 5 different sections here. We're going to break this into 3 different modules. So for module 12.1, we're going to take a look at our series compensation. For module 12.2, we're going to take a look at the design using the Bode plot. And then for the third module is when we're going to take a look at the Simulink and MATLAB applications. So as we begin section 12.1 for module 12, we're covering the topic of series compensation here. So this relates back to our textbook here for these several different sections. So in section 12.1 of our text, there's a couple different things we're going to cover. We're going to cover the hardware implementation, compensator design by root placement, root locus design of compensators, lead compensators, lag compensators, and the design of a lag lead compensator, and lastly, the system type and steady state error. So these are the main topics to cover as you're reading through the sections within your textbook. So as we jump into this section here, we want to cover the basic definition of system compensation. So if we're given a control plan, the procedure of the controller design to satisfy whatever the requirements are for the system is called system compensation. So why do we want to do this compensation? Well, if we have a closed loop system, it has the function of self-tuning. So by selecting a particular value of our gain, our K value there, some single performance requirement may be met. Now, it is possible to meet more than one performance requirement, but it's not always the case. So within this, something new needs to be done to the system in order to make it perform as required. So some modification, some change needs to happen in order to make the system perform as it's required. And this is our compensation. So let's continue on and kind of discuss the difference between design and compensation for an entire control system. So if you're designing an entire control system, the whole controller, you need to design everything to satisfy the system requirements. But if we're talking about compensation, you only need to design part of the controller with the known structure. So within that, there's going to be 3 elements for compensation that we can deal with here. So 1, you have the original part of the system. 2, you have the performance requirement. And 3, you have the compensation device. You take a look at that original part of the system. You say, okay, what needs to be done? What are our performance requirements for this part of the system here? And then you need to design and implement just a compensation device in order to meet the performance requirement as designated within your system. So now I want to get into a little bit more detail with the compensator and discuss how it integrates with our system. So the control systems are used to control the behavior of the system in order to provide our desired output as set forward by the requirements of the system itself or the project that we're working on. So we know there is going to be some desired output, and we're going to need to be able to control the behavior of the system in order to achieve that desired output. So specifications must be achieved in order for the system to perform properly. So there needs to be less errors generated and more accurate results in order to be stable. So generally speaking, we use the gain of the system to adjust first to produce our desired results. But the thing to think about is simply dealing with the gain of the system is not going to work in favor of the system as a whole. So if we increase the gain, it may improve the steady state behavior, but it also is going to adversely affect the transient response. Now this makes the system unstable and it needs to be redesigned. So when we're redesigning the system, some variation is going to be necessary. So such as possibly the addition of an external device. So the use of this external device in the redesign process is defined as our compensation of our control system, and the external device added to the control system itself is known as the compensator. So this is kind of a basic definition of what a compensator is and how it integrates with our control system. Next, I want to take a little bit of time to discuss the structure of the compensator here. So according to the way of compensation, the compensator can be classified into a couple different categories here. So the first category that we're going to discuss here is cascade compensation and feedback compensation here. So cascade compensation, we can see right here, we have our input coming over here, our compensator, our plant, and then we talk about feedback compensation. You can see there's our compensator in line here coming back with our feedback of the system here, and then we have a cascade and feedback compensation given by this here. And we can take a look here, and these are going to be inside the feedback loop. So our cascade and compensation compensation are going to be inside that feedback loop. Now the other type of categories I want to discuss here are your feed forward compensation and your disturbance compensation, where these compensation for feed forward compensation and disturbance compensation are going to be outside of the feedback loop. So you can see here, these are going to be outside of the feedback loop. You can see your feedback loop coming in right there and right there. And you can see that the compensator is going to be outside of that feedback loop. Whereas when we're dealing with cascade and our feedback compensation, they're inside. If this is your feedback loop here, your feedback loop there, your compensator is going to be inside that feedback loop right there. So next we're going to look at different methods for our compensator design here. Now the first method that we're going to talk about is our frequency response method for compensator design. Now the main idea behind this is by inserting the compensator, our Bode diagram of the original system is going to be altered in order to achieve the performance requirements that we desire. So if we take a look at that right here, what we have is you have your original open loop Bode diagram there, plus the new diagram of the compensator, plus the alteration of the gain is going to create and give us our open loop Bode diagram with compensation. So this is for the frequency response based method for compensator design. Now the other method that we're going to discuss here is our root locus based method here. So with this one, our main idea here is when we're inserting the compensator, this is going to introduce a new open loops zeros and poles to change the closed loop root locus to satisfy the requirement. So we're going to look at a little bit more of our cascade compensation. So frequency response based compensation, we have our phase lead compensation, our phase lag compensation, and our phase lead lag compensation. Now our fundamental rule for controller design for a PID controller, each requirement relates to a different region of the frequency axis within our Bode diagram here. So first thing to note about this is a steady state error relates to the magnitudes at the low frequency, whereas the transient response requirement relates to the gain crossover frequency, which is generally going to be a higher frequency. So we're going to take a look at some of the commonly used compensators, our lead compensator, our lag compensator, and our lag lead compensator. So we'll start out here with our lead compensator. So with this here, if a sinusoidal input is applied to the input of a network and the steady state output, which is also sinusoidal, has a lead phase, then this network is called a lead network. So this is for our lead compensator. Now, if we compare this now to our lag compensators, within our lag compensators here, if the steady state output has a phase lag, then the network is going to be called a lag network. And now when we discuss our third type and compare it there, our third is our lag lead compensator. So in this lag lead network, both phase lag and phase lead occur in the output, but they're in different frequency regions. So the phase lag occurs again in the low frequency region, whereas the phase lead is going to occur in the high frequency region, and this is going to be our lag lead compensator. So what are some practical devices that represent these? So some popular lag and lag lead compensators are, if we're talking about electronic devices, we're talking about circuits such as our operational amplifiers, electronic networks, these will be RC networks, and mechanical networks such as our spring mass dampers. So let's discuss some design rules for cascade compensators. So the system is stable with satisfactory steady state error, but the dynamic performance of the system is not good enough. So the compensator is used to change medium and high frequency parts to change crossover frequency and phase margin. Now, if the system is stable with satisfactory transient performance, but the steady state error is large, then the compensator is going to be used to increase the gain and change the lower frequency part, but keep the medium and higher frequency parts unchanged. And third here, if the steady state and transient performance are either unsatisfactory, the compensator should be able to increase the gain of the lower frequency part and change the medium and high frequency parts. So let's take a look at our series compensation. So if we implement this in hardware, a series compensator is going to be a physical device that's going to be inserted in the control system at the output of the controller. So if we look down here for the structure of a system with series compensation here, you can see the compensator right here circled in red is coming right after our controller there. So again, this is a physical device that's inserted in the control system at the output right here, the output of our controller. Now, if this is going to be implemented in software into a digital control system, our series compensator is going to be an algorithm in that case that creates the equivalent of a transfer function. So it's going to be the equivalent of a transfer function inserted in the series of the transfer function of the main control algorithm. So that's the difference between if it's implemented in hardware versus implemented in software, but we can still see physically here, if we take a look at our diagram here, showing that our compensator comes right after our controller. So this is a table from our textbook here that does a comparison of our different types of compensators. I think this is a great reference for us if we're not sure for a particular application what compensator we want to use, some of the advantages and limitations of that. We can come over here to this table and we can see, okay, this is our application here. This is the recommended compensator for that application. Here's our associated transfer function. And then we can also take a look at our advantages and our limitations of using that type of compensator. So if we go down through here and let's just say we have we want to improve our transient response. So we can take a look here and see that there's two different options that we can use to improve our transient response here. We can use our PD compensator or we could use a lead compensator here. So if we're not quite sure which one of those to use, we can take a look over here. Okay, here's our associated transfer functions, and we can take a look at our advantages and disadvantages for each of these. So for our PD, we have these four right here. It's going to require an active circuit. It may increase the overshoot. It may cause noise, and it's better implemented by a rate feedback. Whereas if we come down to here, an active circuit is not required, and it increases the system order by 1 if there's no cancellation. So we can compare these different advantages and limitations and decide, okay, if we're trying to improve our transient response here, which compensator should we use? Should we use a PD or should we use a lead? We'll compare those and decide, well, overshoot and noise are not something I want in my system. I can't have those, therefore I'll need to use my lead compensator. So this is a great table to reference back to if you're trying to choose for a particular application what compensator to use and compare them together. So another option when we're talking about our compensator design here is to use root placement here. So sometimes there is a little bit of flexibility of designing the compensator simply by specifying the root locations. Now this can be done for some order system if the last n-1 coefficients of the characteristic equation are independent functions of the gain. So just another option here for compensator design utilizing root placement. But on the other hand here, the lag compensator is used when the speed of the response in the dampening closed systems are satisfactory, but the steady state error is too large. So as you might expect, this lag lead compensator is used when both the transient and steady state performance must be improved. So that's another thing to consider of when we talked about our table before, when to use our lag lead compensator. So if both the transient and steady state performance must be improved, need to be changed to meet our output requirements, then that's a great opportunity to use our lag lead compensator. So when the performance specifications such as the required time constant, damping ratio, and so on and so forth are given in terms of root locations, but not all the root locations are going to be known to us or they can't be freely specified, the root locus method is a preferred way of designing the compensator. So again, that's something to take a look at when we're determining which method is going to be the best way for us. So as we continue to discuss our lead compensators in conjunction with our root locus plot, we note that the effects of the compensator in our time domain specifications, our characteristic roots, can be shown with the root locus plot. So if we're designing with a lead compensator with the root locus, we can do the following procedure here. So here, for our first step here, we have from the time domain specifications, our time constant, our damping ratio, etc., we need to determine the required locations of the dominant closed loop poles. We're going to determine the location of those poles. Now, from our root locus plot of the uncompensated system, we can determine whether or not the desired closed loop poles can be obtained by adjusting the open loop gain. Now, if not, we can determine the net angle associated with the desired closed loop pole by drawing out our vectors to this pole from the open loop poles and zeros. Then third, we're going to locate our pole and zero for the compensator so that they will contribute the angle required to eliminate the deficiency. Then fourth, go on to compute the required value of the open loop gain from the root locus plot. And 5 here, check the design. Want to double check design to see if the specifications are met. That's going to be important. Did we meet the specifications? That's the whole purpose of adding in this compensator, is to make sure that the specifications are met. But if they're not, then we need to adjust the locations of the compensators, pole and zero, until the specifications are met. So next we're going to discuss the design of a lag lead compensator. So lag and lead compensators are great because they complement each other in the fact that one's going to improve our transient performance while the other one is going to improve our steady state performance. Now there's going to be situations in which one of these might fail to produce a satisfactory design, so that's where a lag lead compensator can be tried if one of the individual lag or lead compensators fails to produce that satisfactory design. Now, in our root locus approach to designing a lag lead compensator, it's a combination of the approaches used for each the individual lead and lag compensators. So the procedure for our approach here for a lag lead compensator is: one, we're going to evaluate our uncompensated system and determine the desired locations of the dominant closed loop poles from our transient performance specifications. Then improve the transient performance with the lead compensator, calculate the phase angle deficiency of the uncompensated system. This deficiency must be supplied by the lead compensator. Then we're going to evaluate the steady state error, and if necessary, improve the steady state error performance with a lag compensator. So again, then we're going to evaluate the transient performance to see if the specifications are satisfied, and then lastly, we're going to evaluate the hardware requirement and check the reliability. So let's talk a little bit about designing a system here. So in an example here, we're going to design a lead compensator with root locus. So let's just say we're designing this here, and we already have an open loop model right here for our plant system right here. Well, one thing we're doing as we start this is we're going to need to think about our design requirements or performance goals that the system that needs to meet. So we talk over here about our requirements, and we can see over here we have things like our rise time, our settling time, our gain, phase margin, damping, things like that. So these are all requirements that the system needs to meet, the performance goals of the system. Whatever these might be, at this point we can kind of see that an open loop system isn't going to be able to meet these requirements here. So from there, what we need to do is we need to implement a closed loop system control around this plant. So that's what we do here down in this diagram right here. You can see now we have our feedback loop programmed in right there. Now, once we have this here, it's up to us. We can choose any compensation technique that we want as long as it meets the system requirements. So we need to go back up here to whatever the system requirements are given to us in the problem that we're working on, the design of the plant that we're doing, whether it's a problem we're working on for a homework assignment or exam, or it's something we're working on for a company, they're going to have these requirements. So we can choose whatever compensation technique we want to use as long as we can meet these system requirements. Now the question we want to ask ourselves is, how do we know which one to choose? And again, we can look at what our requirements are, what our system is as a whole, and why do we choose, in this case here, our phase lead as our compensator. In order to analyze that a little bit more, we're going to take a look at how the phase lead compensator is going to affect the root locus plot here for our system, so the root locus. So let's, for this one here, we're going to draw out a simple two-pole system, and then arbitrarily we're going to put one pole at a -1, and we're going to put another pole at -3 here. So we have this function right here. We have If we take the roots of this here, we get s is equal to -1 and s is equal to -3 for a real simple function here, just for a simple, again, two-pole system here. So we want to take a look at the root locus for this simple two-pole system. Again, that one pole at -1, the other one at -3 right here. We draw out here is our imaginary axis, and then we have our real axis here along the x-axis there. And we put our two poles to the left of our imaginary axis here. Here's our -1 and our -3 for the roots of our equation once we solve this out up here. We put that there, and now you can see over here we have this relationship here in order to find our centroid. So this is how we can find our centroid from that information from our roots. We can say the summation of our finite poles minus the summation of our finite zeros, all divided by n minus m, where n is the number of poles, minus here our m, which is the number of zeros. So in our case here, we have 2 poles and no zeros. So we have this relationship here. We have a -3 minus 1 over 2 minus 0. So the location of our centroid here is -2. So that's right in between, right here on our real axis here, right in between our -1 and our -3 is the location now of our centroid. So this is how we draw out and plot out our root locus for this simple two-pole system. So continuing on with designing this lead compensator with root locus, let's see how the root locus system is going to be affected if we add in a phase lead compensator. So you can see right here, this is where we're going to add in that phase lead compensator. And let's arbitrarily choose here s plus 4 over s plus 5 for this. And we'll see how this is going to affect our root locus plot. So you can see we're still going to have the 2 poles here, one at a -1 and one at a -3. But we've also now added a 0 at -4 and another pole over here now at -5. And if we want to calculate the location of our centroid, we go back up to the same equation here. We plug in our values. Now that we've added in that extra pole at -5 and our 0 at -4, we plug this in here. We end up with a -3, -1, -5 plus 4 all over 2 here. So we end up with is a -2.5 as the location here now. So we can see this right here. This is the location here now of our centroid. So now as we increase the gain of our system, the closed loop poles will now follow these lines instead here. So you can see these yellow lines we have coming up like this here, like that, along that asymptote right there. And so by adding in this lead compensator, we have added stability to our system.